in agriculture, and I met a fellow botanist somewhere during, who's the botanist? Oh, yeah. So, my master's, when I started my education, I did my master's in botany, okay, at the University of Toronto, and then I switched. I went into, it was actually microbiology because I was doing what's called cyanobacteria, which is a form of algae, and that's how I did my work in botany, and so I love agriculture and plants, and so I still do some research in AI for agri-tech, what's called agri-tech, which is the delivery of technology to agriculture, and so I work with coffee plantations in Costa Rica, right? So I bring that up because there's some interest here, of course, as well, in putting AI into that area, right, into agriculture. Okay, yeah, all right, thank you. So I don't know if you, I would suspect you do the same thing here in India. So we do disclosures, what's called disclosures. And that means I might be biased in the delivery of my content, right? And so I share with you, I have two startup companies, Softex Innovations, where I currently run, which is software for the delivery of AI in healthcare. Asage was a medical device company which I exited. So I'm no longer part of Asage. It was purchased. So I'm no longer part of that. I also work with pharma companies, so Novo Nordisk and Sobi. And I also work with medical imaging companies, which you'll get an introduction during the week, Claritas and Analógica Occidental. Interestingly, Claritas, here, the founder is just up the road in Goa. So he's a friend of mine, and his wife has family in Goa. And so he's actually there right now, actually, which is kind of funny, just a coincidence. So that's Claritas, and then the other two I was already introduced. Demeter Innovation Lab is in Costa Rica, and Piano Up is music, and that's just a startup that we worked together with a postdoc of mine, right? Okay, so those are my disclosures. Just be aware. Be careful what you share with me. I might commercialize it. No. I mean, I'm joking about it, but it's true. That's the reason you give disclosures, right? Is that if you're going to put up your hand and share IP, intellectual property, about a project that you've started, you need to know that I'm in a position to benefit from that, right? It never happens because I would never do that to begin with. But it is something for you to know, right? And that's the reason we talk about it. Voila. So this week, you're going to see a whole mishmash of different style of slide formatting and design. And the reason for it is because when I was invited to do this, it was based on a course that I teach at the University of Toronto called AI in Medicine. And it's available to you online. You can access it online through my website, and you can view the videos and the whole thing. It's all yours. So these slides are directly from my course. But then you're going to have a whole bunch of slides throughout the week that are going to be from presentations I give when I'm invited to speak, wherever, right? So it's going to be a mix of slides. I thought, I'll change all the formatting, I'll just use the slides the way they are, okay? There we go. Oh, so, yeah, there's a timer. It's on the timing presentation. I forgot. I should have ruined. Anyway, I'll deal with it. So, let me show you how I got started. Okay, so first of all, I started programming in 1980. That might date me a little bit. And the computer I used, it was actually an 82 or something like that. But the computer I used was a Commodore VIC-20. Does anybody here remember the Commodore VIC-20? Probably not. But that's what my computer looked like. And I had to record, the data was actually on cassettes. You guys don't even remember cassettes, probably. Some of you must remember cassettes, but anyway, it's a magnetic tape, and that's where my programs were stored, right? The programming language was called BASIC programming language. And that, I'm sure here, definitely, you know of BASIC, and I'm sure you've heard of it. It's not used anymore, really, right? But after learning programming, I went into science, and I didn't do any programming until probably my graduate work. And then, as you know, I did a master's in botany, and then I did a PhD in botany, actually, for about 4 years, and then I quit. My supervisor wasn't very happy. And I went into the computer industry and worked in computers. And I was a COBOL programmer, COBOL Kicks, and for MBS, the big mainframes. And India is huge, or was huge for COBOL. COBOL programming in India was just massive. But that's where I learned to program. Now, the reason I'm showing you this, that's an iPhone 6. I would suspect nobody here has an iPhone 6, right? Because that's old. That's old stuff. You have an iPhone 6, okay, that's sad. That's right, you need to upgrade, right? I'm kidding. But, you know, that's the challenge of these days. Does anyone recognize what this is? Anybody? So this is as tall as me. It's about 6 feet. That is a supercomputer. It's IBM's Deep Blue. And if you look at the size of your phone compared to Deep Blue, that's the comparison. Okay? So, in 1997, who plays chess here? No chess fanatics in the room? Really? Really? Yeah, a little bit. So do you guys remember who Garry Kasparov was? Is? He's still alive? Right. So one of the top Russian chess masters ever, right? And that computer beat Garry Kasparov in 1997. And that was a big deal. That was a big deal because a computer to beat a chess master was a big deal. Now, everybody understand what a gigaflop is? Gigaflop? No. So how do you measure compute power? You measure it in flops, okay? Gigaflops, megaflops, petaflops, okay. So I'm asking you here, one of these devices has 11 gigaflops and the other one has 142 gigaflops. So just remember, gigaflops is a measure of compute power. So which one do you think has the larger gigaflops? Anybody? I mean, it's kind of I'm leading you into this question. So, can anyone guess which one has the larger compute power? Yeah, the mobile phone. And actually, 142 gigaflops is a bit sad. Because it's a lot more. I mean, the iPhone 6 is even less than 142. 142 is probably close to where the iPhone is. Probably a bit more now, 180, something like that. The iPhone 6 is like in the 50s or something, like much less. So just imagine you are all walking around with a supercomputer in your pocket. So for you younger generation, you may not appreciate that because you never had that problem. When I was working on the VIC-20, the compute power was ridiculously small, and the memory was even smaller, right? So what I was able to do in BASIC was practically nothing, right? But now we all walk around with a supercomputer. So why is that great? Well, because, and Edward Fredkin from MIT, one of the godfathers of AI. So yes, of course, Geoffrey Hinton, who won the Nobel Prize for it, is well recognized for it. But there are others who contributed to the development of AI over the time, and one of them is Edward Fredkin from MIT, and he quotes, and this is just a fun quote, just to warm you guys up a little bit, right? So there are 3 great events in history. 1, the creation of the universe. 2, the appearance of life. The third one, which I think is equal in importance, is the appearance of artificial intelligence. Now, he made this quote many, 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 many years ago, right? Why do I say it? Because, think of it, he was just joking, really. I mean, kind of. The appearance of artificial intelligence is really going to be very impactful. And no matter what you think or do, it will be. So many people think, oh, well, if we pretend it's not there, it's going to go away. It's never going to go away, okay? Oh, oops. My slides are on timers, that's why, sorry. So, what I would like to encourage you to do, and once again, this is an older quote, is to take into account this quote, physician. We need to take the artificial away from our embrace of technology. The term AI should stand for augmented intelligence, not artificial, but augmented, so meaning it's helping us. Jeffrey Hinton just recently, like a couple of days ago or something, stated that there's a risk that AI is going to exceed our capacity, right? It's going to exceed our intelligence. It's possible. It's very possible. I don't know when. I don't think it's going to be in our lifetime, maybe. But it's definitely something to think of. And you need to understand, how to apply AI. So if we continue to apply it as a tool, even if it ends up being of higher capacity than our own intelligence, it's still a tool. Okay, it's under our control. And that's what Jeffrey Hinton was alluding to, is that we need to retain control by making it, appreciate us as humans. Right? Anyway, I don't know if you caught it on the news, but. Okay, another quote. I don't see AI as competitive, but rather as an augmentation and expansion of radiologists' capabilities. I'm going to talk a lot about radiology because inevitably I'm in medical imaging, okay? So that's the way we see AI helping radiology. It's not to replace the radiologist, it's to provide the radiologist with a wonderful tool, okay? So let's just go through a little bit of definitions just to get you guys going. So why are we so smart? We've survived billions of years of evolution, right? We are dominating the world. We are, right, in terms of a species. We do learn from our mistakes. It's very difficult to avoid, very difficult to admit we made mistakes, but we do, and we learn from it. And we adapt ourselves to perform better, right? We adapt. Inevitably, we have to adapt, right? And so that is, in essence, why the human race is considered smart. Right? So what's artificial intelligence, right? So intelligence is the ability to acquire and apply knowledge and skills. Okay, boring definition, but that's essentially one of the main definitions for intelligence. In McCarthy, in 1956, at a conference in Dartmouth, United States, coined the term artificial intelligence with some colleagues. It wasn't just him, he had some colleagues as well. That AI is the science and engineering of making intelligent machines. That was the start of the term artificial intelligence, okay? Now, if all of you just need to remember one thing about how to describe AI, you can just remember 3 words: store, compute, and learn. Okay? That is what has brought or enabled us to benefit from AI. So storage, AI is very data hungry. Machine learning is very data hungry. So you need the ability to store data. If you do not have the capacity to store vast amounts of data, then you're going to be limited in what you can do in using machine learning. Compute, you need the compute power, and we just went through that. The reason that Jeffrey Hinton is finally successful with his lifelong work in machine learning is because of this, okay? When he started publishing artificial intelligence and machine learning and neural networks in the late 70s, early 80s, a long time ago. But he was never successful because he never had the capacity to actually get it to work at scale. And so that's the reason he won the Nobel Prize, because he hung in there. Instead of saying, no, I'll do something else. He continued. And because of that, he showed that it was possible. Now the last piece, if you have storage and compute, that's great. But for machine learning, or artificial intelligence, you need the ability to learn. Because if not, it's not machine learning, if there's no learning. Right? So there has to be the ability to learn. Okay? So if anybody at a party or something asks you, what is artificial intelligence or machine learning, just remember those 3 words: store, compute, learn. Okay? Those are the requirements. So I'm not going to bore you with this, but this is kind of the AI spectrum. It's definitely more complete than this. This is probably a little dated. But essentially you have, obviously, the machine learning area of it. which we'll go over this week, and you guys know it, I'm sure, which is supervised, unsupervised, learning and reinforcement learning. Natural language processing, which is huge now, right? NLP is just huge. I mean, now I don't want to single you out that way, but if you don't use ChatGPT, I'm just going to say, why aren't you? You should be, right? It's not perfect. Absolutely, it's not perfect. But what a fantastic tool to have in your pocket. My God, right? So if you're not using it, because I don't believe it. When I ask, when I'm lecturing, and I'll have like halls, huge halls, like 300, 400, 500 people, and I'll ask them, who here does not use ChatGPT, right? And you always have people put up their hand. I don't believe it. I think they're closet ChatGPT users. They say, oh, I don't use it because it's terrible. But then in private, they use ChatGPT. How could you not? How could you not? Okay. Expert systems, vision, right? Image recognition, machine vision. We do that. Speech, that's another huge area, right? Speech recognition. Speech to text, massive stuff, right? All of the translators, Google, there's lots of stuff, right? Planning and robotics. Planning's boring. Boring, right? Who wants to do planning? Ugh, right? But it's so impactful. It's so impactful. The use of artificial intelligence for doing mundane, repetitive tasks like planning is so impactful. And that's something you should consider. Don't always go for the rare disease detection. Sure, you're going to help the few people that have a rare disease, but no offense to the people that have the rare disease, but you're not really helping lots of people, you're helping a few people, okay? Robotics, of course, very cool, and I can share with you guys, in the Philippines, I was teaching robotics. It was a lot of fun. Who here has heard of the term disruptive technology? Do you guys know what a disruptive technology is? Who does? Put your hand up. Come on. Nobody's heard of disruptive technology? Okay, good. Awesome. Somebody. Yay. Yeah, there we go. Someone who's shy over there. So disruptive technology is used in the market. It's to do with the sale of product in the market, essentially. And how you describe it is very easy. It's essentially a 10 times improvement in performance of a product, whatever the performance is, in less than 10 years. So if you have a 10-fold increase in performance in less than 10 years, that's called a disruptive technology. So, performance, time, and then you have what's called quality use, right? This is a demanding use because you need the performance. This is a low quality, low performance. Disruptive technology is one that's just exponential over your 10 years. So what are the examples? These are North American terms. I suspect Blockbuster is not a company that was in India. Maybe, I could be wrong. But do you remember the days when you went to watch videos at home? You rented the DVD or the video cassette, right? That is an example. That company, Blockbuster in North America, went bankrupt because it was taken over by Netflix. I suspect you have Netflix in India? Of course. So Netflix was streaming, and it just wiped out all of the CD, DVD, and VHS recording, right? Gone. Right? Now you stream. Everybody streams. You watch it on your phone. So there's an example of a technology. The other one's Kodak. Dating myself again, but back in the day, you used to have to use film to take pictures. And Kodak was the biggest company on the planet that produced film. And when digital cameras started to make their appearance, Kodak said, nah, that's not going to happen. And of course, as you know, all pictures now are taken on your phone, right? So Kodak went bankrupt, right, for the same reason. So there's another example of a disruptive technology. So the use of digital photography was a disruptive technology. And AI, as you can imagine, is already a disruptive technology. Absolutely. Even though the term has been around since 1956, the use of AI is only very recent. Right? Okay, the Industrial Revolution, you guys all learned this in high school, right? Boring stuff. But just to understand where we are today, this is the 4 steps of the Industrial Revolution. We are in cyber physical systems, the Internet of Things. Okay, that's where we are. Networking is where we're at. Okay, and it's because of that that we can share data, we can collect data, we can use data. Before this, we did not have that capacity. But you need that data if you're going to train it. Data revolution. So today's just an intro, right? So during the week we'll go into detail. But essentially, who remembers what was called big data? No? Come on. Yeah, come on. Big data wasn't that long ago, right? Big data was probably like 2013, 14, 15, right? Big data was this concept that we have tons of data. We have a lot of data. How do we deal with data, right? And so the 3 V's, there's actually 5 of them now, or 7, some people use 7. But the 3 main V's is volume, velocity, and variety. So it means, volume means lots of data, velocity means how much data you're getting, on the pipeline, and variety means how many different types of data. So that was what was classified as the big data problem. And then AI kind of came out and just squashed big data, okay? I'd say AI started appearing kind of 2015-ish, like that, right? 2016. And why is that important? Because of this variety. So we're gonna talk about that in machine learning. So who's heard of multimodal models? Anybody? Who's worked with multimodal models? So, right, the purpose of multimodal is to deal with this problem, the variety of data, inputting different types of data into a single model and fusing it. Not an easy task, okay? But it's possible now. So, AI, which we know is the capability of machine to imitate intelligent human behavior, that's what we're trying to work on, and it uses computers to model intelligent behavior, right? With minimal, intervention from us. We do want to automate, absolutely, but we still need to be part of the process. And I'm not saying that, it's a philosophical question. I'm not saying that we should be part of the process from a philosophical perspective, which is true. But it's also, we do need input from humans, okay? And why is that? So a lot of you might be thinking, why would we need humans? Like these machine learning algorithms are fantastic, right? They can learn on their own. So why do we need human input? Anybody? Why would we need human input? Sure. But why do we need to give it data? Couldn't it collect data on its own? Very good. So that's exactly right. Is we need an algorithm that's going to serve us. That's the purpose of the algorithm. It needs to benefit us, right? It needs to be in tune with us, integrated with us, because that's its purpose. If not, it would be all on its own, doing its own thing, and who cares, right? And so that's a very important concept that many engineers in particular, because engineers are very into the technology, lose sight of that, okay? In the sense that they need to include in their work, why are they building that algorithm? Why does the algorithm need to behave in such a way? What is important with the output of that algorithm? Because sometimes the answer that an algorithm gives is not useful to us in society. Just because you can do it doesn't make it useful. Okay? So that's essentially what I'm saying here, right? So, if machines simulate what humans do, would they have our intelligence? So, probably. Like when you think of intelligence, right? Probably. It's possible. Is it coming? Yes. Is it here now? It's close, maybe. Right? But will the artificial intelligence ever be human? Now, we could just talk a whole week about that topic, but what do you think? Do you think artificial intelligence will ever be human? There's a really easy answer for that. No. Why? Not because it's not going to be smart enough. We know it will be smart enough. It will actually exceed our capacity easily. So why will it never be us? Yeah, but you saw the movie Terminator, right? Skynet's going to take over, right? So, but why? I'm just joking. I don't think it will take over. But why can it not be human? Yeah, so can machines.
Those are the data on which it's trying to talk about evidence.
Who's in biology here? There we go. So we'll talk about that too. You're right. Reasoning's not there yet, but it's coming. I think it's possible. But why will it? Even if you achieve general AI, which is reasoning, why would it never still be human? No, it will think, it will react. No, maybe general AI would be emotion. You guys are great. You're bringing up we're going to cover all that. But yes, that's great. But no. Nah. Some people have already said they do. They got fired from Google. Remember? That was a few years ago. There was an employee at Google who got fired for that, for saying that AI had a consciousness. So. Yeah, it's mimicking human behavior, sure, but so why can't it be human, ever? It will never be human. Why is that? So it's a biology. Yeah. No, you can imitate that. Recurrent networks. What do you all do every day? What do we just have? We just had a snack and tea. Why did we have to have a snack and tea? Because we're human, right? We have a body. We are biologically made up. Artificial intelligence will never have a body. They will never be born. So remember that. AI can absolutely exceed us. But it will never be human because it doesn't have a body. So how do you work your input in machine learning? You use data, numeric data. Even if it's imaging, it's numeric, right? It's pixels. So it's all numeric data that's being fed into a model. How do humans process? Neurons. But how does it collect the data? Is it collecting numeric data from a spreadsheet? Sensors. That's exactly right, sensors. So artificial intelligence is not going to have access to our human sensors. We could potentially connect human sensors to a machine, maybe, and they're trying to do that through that ridiculous link. I'm not even going to go there, but they're trying to do that. Okay, fine. Maybe in the future there'll be a connection. But don't forget, we are human. We eat, we sleep, we have limitations. That's what makes us human. Yay, let's celebrate that. And AI is never going to happen. It's never going to happen. Right? So I'm going to go through this quickly because I suspect most of you know this story. Do you? Right? Neural networks. So neural networks is based on the human brain. Did you guys know that? You must have known that. So when you say you're working with neural networks, you're actually working with something that was developed in order to mimic the neural structure in your brain called synapses. Okay? And so the neuroscience is how it developed it. And essentially, it's a complex system of neurons. And, you know, this is a biology lecture, and I don't want to necessarily go into too much. But, you know, it's how the neurons connect and how they learn, which is what was applied to machine learning. Okay, so the neural networks by Jeffrey Hinton and others for this learning, right? So the artificial neural network, ANN, which was the beginnings of the neural networks, they loosely follow, right, this simple process of information in the brain, okay? And essentially, the question, of course, is how does it store that information? Right? And so that's how the neural. So how do neural networks store information? How is neural networks? How is it storing information? In the weights, in the weights, in the weights, right? So your brain does the same thing. So McCulloch and Pitts actually described how this worked in 1943. What? That was at the same time as Turing, right? Turing, right? So this has been around for a while. And this question, of course, is that if you repeatedly stimulate a neuron, it learns that way, right? So it's more heavily weighted, just like in a neural network, right? And this is the weights in artificial intelligence. And this is how the neural network developed by Jeffrey Hinton won this prestigious computer vision competition, ImageNet, in 2012 by a massive margin, right? Dropping from 26 to 15%, which at the time was just spectacular. 2012. Remember, this was 2012. And that was the beginning, right? In 2022, that was the birth of ChatGPT, right? In these generative pre-trained transformers, right? GPT, right? And OpenAI released it in 2022, essentially, and then, you know, it's been around. They were working on it years before that, but that's when it was released and everybody got access to it, right? And this is, you know, obviously it's the largest neural network that's ever been released and worked on, okay? So, as I said, in the neural networks, when we, you know, I'm not, like, you guys are probably as knowledgeable as me in this, easily, right? But I wanted to share this with you so you could make a connection between what you're working on mathematically and your brain. It's just nice to think, oh, interesting, that the process that we're working on is similar. That's what's going on in our brain. So this is just a way of remembering. This is a funny way of remembering. Is that the nodes in your network are comparable to old men or women. I'm an old man, so I thought I would share that. Here, with hearing difficulties, right? Standing at a distance from each other, right? So the farther you are away, if you can't hear, then you have to yell louder, right? And so they only hear when the sound is loud enough, and that is how it works in activation in nodes. Okay, that's the weighting, right? So here's your dendrites, which is your input, right? And then your cell body and your axon, and then your terminals, which is your out. It's very similar to your node in a node. It's not audible. Oh, sorry, it keeps falling out. Sorry.
Little, yeah.
Yeah.
Yeah, it's online.
Oh, online. Oh, sorry. See the poor online people. Okay, no problem. That better? It's a bit creepy, but it's okay. Okay, so the reason I'm bringing this up is just so that you understand how weighting works in neural networks. Okay? So the weighting in neural networks, you need that impetus to trigger, right, in a node, and that weight, right, which is essentially programmed into your training, is what is shared in a neural network. Does that make sense? I just wanted to bring to your attention how it works. So you have many, 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 many nodes in a neural network, and each node has to behave, right, with your input, what's called a bias, so we won't go into the math of that, but you need a bias, and your activation, right? Your activation function and your output, and it goes on to the next layer, and the next layer, and the next layer, and the next layer, right? So I just wanted to bring that to your attention because very often people will use something, but they don't really get how it works, right? And that's okay. I mean, that's okay. It's funny, we were talking about that with, Dr. Shikar at dinner last night. And it's okay. I mean, you're welcome to use technology without understanding it. That's all right. But sometimes you have to kind of stop and think about it a little bit. And the reason for that is because if you want to be innovative, then you do need to understand how it works. And I'm not minimizing it. I'm not saying like, oh, you're just applying it, because that's most of what I do. But it's good to know a little bit more of how it works, because then you can be a little more innovative and say, how could I change how I use this just a little bit so I get a better result, okay? And by doing that, you improve your neural networks, and that's exactly how all of these new technologies are coming out weekly. Different models, and you can't even keep track. There's so many changes, right? And that's how they're coming out. Okay. So why machine learning? I don't even know if I have to go through this. I mean, you guys know, right? There's just so much we can do: computer vision, speech recognition, medical image analysis. This is systems that are more. Stuff that you are more in touch with. So spam detection, how annoying is spam, right? But all of those filters need algorithms, and so they contribute. Robot movements, that's just really cool, right? If you're into robotics. Is there much robotics? There's a lot of area in robotics, right? Once again, working in robotics is a little bit like looking for that rare disease. Is robotics really going to change the world? I don't know, maybe. But I'd rather think of the application of AI that's going to improve processes, right? We were talking to some colleagues and talking about, sensor in the gearbox of cars. And you think, oh, God, that's so boring. But actually, that's pretty cool, right? Because the ability to understand, and for safety, for instance, or for reliability, or for, all of the above, is kind of important, right? You don't need necessarily a robot to fully automate something we do. Maybe you do. Industrial robots are very important, of course. But just keep it in mind, right? In terms of perspective, right? Machine learning can find patterns in large amounts of data. I think that just kind of sums up machine learning, doesn't it? That's essentially a lot of what it does. It's just looking for that pattern, right, in lots of data. Because that's, I'm a statistician, so I'm unfortunately going to bore you quite a bit with stats this week. But I have to, because, understanding statistics is kind of important. And so even at this level, sorry, keep moving forward there. I will fix that. No. This part, finding patterns in large amounts of data. Why can't you find patterns in a small amount of data? Why can't you do that? Why do you need so much data? Like, it's annoying, isn't it? Like, if you're a machine learner, it's so painful that you have to download these massive data sets in order to make anything work. What? So why do we need so much data? Better results. See, there is exactly what all engineers answer. Better performance. It's true. However, I want to know, statistically, why is it important to have such a large training set? So yes, of course, better performance, of course. But why do you need more data to get better performance? Very good. Excellent. So all data, all features have a distribution because there's variability in the data. If there was no variability in the data, would we need statisticians like me? No. Would we need machine learning? No. Why is that? Because I could sample one single representative sample from any distribution. Well, it's not a distribution anymore, is it? The distribution is a single point, right? And I would know exactly what that disease looks like. I wouldn't need to do training. So without variation, without variance, without variability, you wouldn't need any of this. The only reason we need so much of this is because there's so much variability, which is such an important concept. And so many machine learners come to me and complain about the variation and the variability. Right? Because if you have less variability, you train much easier. Correct? So why is that not a problem? Right? Because life would be so boring if we were all exactly the same. It's because of this variability that it's interesting. So don't complain about it. Enjoy it. It's a challenge for you as a machine learner, but that's okay. Think of it. If there wasn't that challenge, you wouldn't be a machine learner. You would not have a job. You would not be a student. So keep that in mind because it's important. All right. So machine learning, what is it? Once again, we've kind of talked about this. I'm going to get through it because I don't, we could be here all afternoon. But, essentially, we're looking for patterns in existing data. We're making predictions and decisions, right? We have a set of algorithms which are called models in the world of statistics, right? So if you call it a model or you call it an algorithm, essentially the same thing, okay? There is a difference between classical statistics and machine learning. Does anybody know, can anyone guess at that? So classical statistical modeling versus machine learning. When do you use statistics first and foremost? When do you think of using statistics? Rule-based, sure, excellent. But why do you use statistics? What do you report with statistics? Not bad. Not bad. Yeah. So, okay. So, but there's a word that's missing on that one. So I get it. So you're trying to say that, machine learning is very much for what could happen in the future, right? So that's prediction, correct? Excellent. That's very true. That's excellent. When you first think of statistics, you don't generally think of regression for a prediction. You can certainly do that, absolutely. Right? But generally, when you think of statistics, you always think of the mighty p-value, which is comparisons. You're doing testing. You are testing whether there is a statistical difference, significant statistical difference between something, groups, right? Uncertainty, right? Dealing with uncertainty, right? And all of that is based on random sampling, which ties into distributions. You must know the distribution of your data. Those are assumptions that need to be met. But that is what statistics is typically used for, not for prediction. I mean, it is, don't get me wrong, of course. You do prediction in statistics. But more often than not, you use it in order to test something. So be careful. In machine learning, you don't do that. You don't do testing in machine learning. And that's actually one of the problems, is reporting your results with certainty. There is no confidence limits in machine learning, is there? You can't report, here's the value, with a confidence limit. Right? So there's a lot of work currently that's being done in order to do exactly that, is to report confidence with your value. Because if you were to predict, let's say, you have a mole on your arm, and you're concerned it may be malignant. So what do? You whip out your phone, because it exists, and you take a picture of your mole, and it tells you whether or not the margins of the mole are rough, which would represent the possibility of a malignant mole, correct? Wouldn't you like to know, because you guys are all very well-versed machine learners, you realize that all algorithms have error, correct? So wouldn't you like to know if when that algorithm told you it was malignant, wouldn't you like to know how confident that algorithm was? So that's the challenge, right? Is how do you express that confidence? Because you don't know if it was a false positive. It's not expressed. It doesn't tell you. And even if it says this algorithm is 91% inaccuracy, does that help you appreciate if your answer was a false positive? Nope. Doesn't, does it? So it doesn't make you feel any better, does it? You as the machine learner who developed the algorithm is going to say, hey, I did a great job. I have an algorithm that's 91% accurate. You know, I celebrated when I got that, right? But the user is going to say, I don't care. I don't care what you say. All I want to know is, do I have cancer, yes or no? But you can't tell them that, and that's a problem. So there's the crossover between statistics and machine learning. That's very important. And there are ways you can express confidence, right? So you can run there's way, we can talk about that if you want. I don't have it in my lectures, but we can certainly talk about that in terms of how could you provide confidence in terms of your algorithm. So there are ways to do that. Okay? Okay, so that's good enough for that. Okay, so yeah, so algorithms are not magic, right? And so when you're training, what essentially you're doing, which I'm sure you all know, is you're trying to minimize error, correct? So you have this wonderful cost function. There's actually a loss function, a cost function, and an objective function. Do you guys know that? They're all kind of the same. It's just that whether it's for one, it's for the algorithm, or it's for, right? Okay. So I won't go into that. But essentially, it's all the same idea, right? You're trying to penalize mistakes, right? And you're trying to encourage the algorithm to change its weights, right, in order to improve. So what's called minimizing your cost function. You want to be able to improve your algorithm by changing the weights. So I'm not going to bore with you guys with this because you guys are probably all pros with this. But in the neural network, that's essentially what you're doing, right? And we're going through it. So I'm sure you guys have all seen this. You guys are all grad students, so you're probably like, oh my God, I've seen a lot of this, right? But essentially, the reason we need this is just to show that the perceptron is probably the base. And we iterate through training, right? I always come back to the error because you need to understand what error is. So there's lots of error. What different types of errors do we have? Different types of errors, right? There are two big groups of errors. One's called systematic error, and the other one's called random error. Those are the two big chunks, but there's a whole bunch of different things that can contribute to error, right? And you need to be aware of that, because don't forget, when you're training, if you don't understand where your error is coming from, you're not going to be able to help the algorithm. So systematic error is called bias, right? It's another word, it's called bias. That is something that is a huge problem in machine learning. Especially, here is a classic one, and I'll be talking about it, is the sex, right? So male and female. I won't even go into gender because gender has a whole bunch of other different classes, right? But sex is only two, and that's not going to change. It's called sex at birth now, right? So you call it sex at birth now versus gender, right? So gender is a construct, right? And sex is biological. So just in this room alone, is there bias? If I were to train an algorithm on everybody in this room, on physical features of everyone in this room, would there be a bias? What do you guys think? Would there be? Yep. Because there are more males in the room than females. It's actually refreshing to see that it's pretty close, actually. It's not bad. Maybe I'm just guessing like 2/3 to 1/3, or maybe even better. So, typically, very often in engineering, there's very few females. But it's changing, right? But that's a huge concern because there are biological differences between us. And so if you train out in healthcare, by the way, don't forget, everything I talk about is in healthcare, right? So if you don't take into account features like that, then the application of your algorithm afterwards is going to be problematic. There's going to be error. It will not be as generalizable. So you have to keep that in mind. And so that's where the concept of error comes into play. Okay? Sorry, I just kept running, but that's what I just wanted to share with you, this error for the weights. That's the purpose of it, and there's several sources of it, right? So keep that in mind, right? So back propagation, I mean, no surprise, you guys all know that's the, it's the Nobel Prize for it, right? So is it important? Absolutely. But the one that you want to think about as well, very important, is the optimization of algorithms. Okay, optimization is key. Because that's where you're going to squeeze out a better algorithm, is by better optimizing how you train. All right? Just doing fixing the error is going to be, it's not as easy as you think. And all of you that have done it, you understand that. So optimizing, finding the best solution is going to be, and these are just classic approaches to optimization. But there are so many other ways now to optimize, and you can actually develop models to optimize. Have you guys done that? Right? Have you heard of that or done that? So you can actually train algorithms to optimize other algorithms, right? Because it is so tricky, all those hyperparameters. I don't know which ones to change which way and what, right? So you can actually train an algorithm to optimize that. Okay. Okay, so just to take a little bit of a breather on concepts. This is outdated already because it's changed so much, but these are the classic approaches. And the reason, I haven't even put reinforcement learning because in our world of medicine, reinforcement learning, and we'll talk about it during the week, is not a huge area. Like reinforcement learning in medicine is not huge yet. I don't know, maybe it'll change. But right now it's all supervised learning, mostly supervised, some unsupervised, some reinforcement learning. But the ones that you're going to encounter the most, as you know, machine learning comes under data science. So does statistics, by the way. So statistics will come under data science. Machine learning comes under data science. Deep learning, deep networks, neural networks, comes under machine learning, right? The big ones for us in supervised learning is classification and regression. Those are the two biggest kind of hits for us, because in medicine, physicians tend to work in binary. They like to know yes, no. Is there a disease? Yes, no. What is it? Regression definitely happens as well, okay? Decision trees especially, with neural networks. Ensemble methods was really hot like a while ago. Now it's, not as much. And then just predicting, let's say, months or, an output of like survival in months or years, and so that's regression, okay? In medicine, that's what we tend to do. In unsupervised learning, which is a really interesting area, I take particular interest in unsupervised learning, but is it useful? Like in research, yes. In application, not as much, okay? Because most of it is clustering, okay? And can you cluster your data without formal labeled features, right? You're leaving it, it's data-driven. You're leaving it up to the algorithm to decide the clusters. Very interesting. Is it useful? Less so, okay, for its application, right? I mean, I enjoy it, and you learn a lot from it, but, can you actually use it in practice? Not so much. Okay. Neural networks is the key. We've already talked about that. So how to choose a model. So there's the tricky bit, and it's getting harder. So it was easier before, now it's harder. And the reason for it is because there's so many. There's just so many different ways to do the same thing. that how do you choose, right? So you can go through these steps, which is clear, identify the type of problem, of course, what are you dealing with, what's the problem you're dealing with, what's the data you have available. This almost sounds like your project, right? What data do you have available? How complex are the relationships, the region of interest, for instance, in my world of medical imaging? And how scalable is it, right? So, how generalizable is it? How scalable is it? Like, where are you going to use it? Are you doing it only in Mangalore, or are you going to, develop it for the whole of India or the whole world, right? And so that's the challenge of it. As I said before, AI, machine learning, deep learning, data science holds artificial intelligence. The deep learning bit of it, it was so hot, like a few years ago. But I've got to tell you, deep learning now is just, there's so much other stuff now that, it's still very important, don't get me wrong. I mean, I do it all the time and I love it. But, it's not as talked about as much. Have you noticed that, right? It's just almost like a given. Oh yeah, of course I do deep learning. Like, who doesn't, right? The problem with deep learning is the size of the algorithm, right? The number of parameters in the algorithm is just massive because of all the layers. So many layers. That's the reason it's called deep learning, because there's the depth of all the layers. And that's a challenge for delivery, for scalability. So there's one to think of, is how scalable your solution will depend on who can use it. So not everybody has a supercomputer to run your algorithm. And so that's a limitation. Okay, so you have to think about, for instance, the car, example, is what's the capacity of that computer that's on board your vehicle? Can it use a massive model for inference, right? What's the latency in the response is a problem. Could you just wiggle the mouse there for me? Thanks. Right, so that's definitely a challenge, right? Oh, sorry, it was me. Oh, look at that, we're at the end. So that's just something for you to think about, right? Is how do I actually benefit from the algorithm? Just because you create, that's a huge problem for academics. And I'm at fault too. I try not to do it, but I'm at fault too. Is, you have students that come on board and you have this lab, yay, fantastic, welcome aboard, you're my master's student, fantastic, we're going to think of a project for you, we go through all the steps, what data do you have, what's the problem you're addressing, and then you work for 2 years on your project and you end up with an algorithm and you get 93% accuracy. And you're like, oh my God, that's amazing, I just got my master's, I'm done. Like, fantastic, right? Who uses that algorithm? Who's going to use your algorithm? Probably nobody is going to use your algorithm. Nobody is. Right? That's a shame. And so I'm not saying that foundational research is not important. It is. It's crucial. What we do in academia is foundational research. But if we lose sight of its application and its benefit to society, we're not going to do as good a job. You know what I mean? Like, I get it. You want to just do pure research. I get it. But if it's not useful, who really cares other than you and your supervisor? And that's a bit of a shame. So I'm not saying don't do foundational research. Of course not. Absolutely do it. But keep in mind how you would apply it, right? Because sometimes the algorithms you come up